Welcome to the world of code craftsmanship, where writing elegant, robust, and adaptable software is an art form. And like any art form, it requires a set of guiding principles to create something truly exceptional. Enter solid principles, the master key to unlocking the full potential of your code. In this video, we'll take a journey through the 5 solid principles. Single responsibility, open-closed, Liskov Substitution, interface segregation, and dependency inversion, and discover how they can transform your code into a work of art. We'll explore each principle through the eyes of a master craftsman, with inspiring examples and hands-on demonstrations of how to apply them to your own projects. So, put on your thinking caps, grab your favorite coding tools, and let's create something truly exceptional with solid principles. Solid principles are a set of 5 design principles used in software development to make code more maintainable, flexible, and robust. These principles help developers create code that is easy to understand, modify, and extend. The SOLID acronym stands for S. Single Responsibility Principle, SRP. O. Open-Closed Principle, OCP. L. Liskov Substitution Principle, LSP. I. Interface Segregation Principle, ISP. D. Dependency Inversion Principle, DIP. In this article, we will go over each principle in detail and provide examples to illustrate their usage. Single Responsibility Principle, SRP. The Single Responsibility Principle, SRP, is one of the solid principles in software development. The principle states that a class should have only one reason to change, or, in other words, a class should have only one responsibility. This means that a class should be responsible for only one thing and should not have multiple responsibilities or reasons to change. By adhering to the SRP, we can create code that is more modular, easier to understand, and easier to maintain. When a class has a single responsibility, it becomes easier to modify, extend, and test that class, since we only need to change the code related to that specific responsibility. For example, consider a class that is responsible for processing orders and generating invoices. If we change the way we generate invoices, we would need to modify this class, even though it is not directly related to order processing. This violates the SRP since the class has multiple responsibilities. Instead, we can split this class into 2 separate classes, one for processing orders and one for generating invoices. This way, we can modify each class independently without affecting the other, making the code more modular and easier to maintain. Here's an example of a class that violates the SRP. In this example, the employee class has 2 responsibilities: calculating pay and saving employee data to a database. To adhere to the SRP, we can split this class into 2 separate classes, one for calculating pay and one for saving employee data. By splitting the responsibilities into separate classes, we can modify each class independently without affecting the other. This makes the code more modular and easier to maintain, as well as making it easier to test each class separately. Open-Closed Principle, OCP. The Open-Closed Principle, OCP, is one of the solid principles in software development. The principle states that a class should be open for extension but closed for modification. This means that we should be able to extend the behavior of a class without modifying its source code. In other words, we should be able to add new features to a class without changing its existing code. The OCP is important because it helps us create code that is more maintainable and less error-prone. When we modify existing code, there is a risk that we may introduce bugs or unintended side effects. By following the OCP, we can avoid this risk by only adding new code instead of modifying existing code. One common way to follow the OCP is by using the strategy pattern. The strategy pattern is a design pattern that allows us to define a family of algorithms, encapsulate each one, and make them interchangeable. This way, we can define a set of behaviors in a class, and then use different strategies to change its behavior at runtime without modifying the class's code. Here's an example of a class that violates the OCP. In this example, the payment class has two payment methods, credit card and bank transfer. However, if we want to add a new payment method, such as PayPal, we would need to modify the payment class. This violates the OCP since we are modifying the existing code instead of extending it. To adhere to the OCP, we can use the strategy pattern to encapsulate the payment methods into separate classes. In this example, we've created separate classes for each payment method, and we've encapsulated the payment processing logic into each class. We've also introduced a payment_processor parameter in the payment class constructor, which allows us to pass in a specific payment processor at runtime. By using the strategy pattern, we can add new payment methods by creating a new payment processor class and passing it into the payment class constructor. This way, we are extending the behavior of the payment class without modifying its existing code, which adheres to the OCP. Liskov Substitution Principle, LSP. The Liskov Substitution Principle, LSP, is one of the solid principles in software development. The principle states that objects of a superclass should be replaceable with objects of its subclasses without breaking the program's correctness. In other words, a subclass should be able to substitute for its superclass without causing any unexpected behavior or errors in the program. The LSP is important because it helps us create code that is more flexible and maintainable. By following the LSP, we can write code that is easier to extend and modify without introducing unexpected behavior or errors. To understand the LSP, let's consider an example of a class hierarchy. In this example, we have a rectangle class and a square class, where the square class is a subclass of rectangle. The square class overrides the __init__ method to ensure that both the width and height are the same, making it a square. It also has a set_side method to set the side of the square. However, this class hierarchy violates the LSP since a square object cannot be substituted for a rectangle object without breaking the program's correctness. Specifically, the set_side method of the square class changes both the width and height, which is not possible for a rectangle object, where the width and height can be different. To adhere to the LSP, we can refactor the class hierarchy to use a shape class as a superclass and separate the rectangle and square classes. In this refactored code, we've separated the shape class as a superclass and defined the get_area method as an abstract method. This ensures that any subclass of shape must implement the get_area method. We've also implemented the rectangle and square classes as subclasses of shape and implemented their own get_area methods. With this new class hierarchy, we can now substitute a rectangle object with a square object, or vice versa, without breaking the program's correctness. The square object no longer has a set_side method, which ensures that it follows the same interface as the rectangle object. Interface Segregation Principle, ISP. The Interface Segregation Principle, ISP, is one of the solid principles in software development. The principle states that no client should be forced to depend on methods it does not use. In other words, a class should not be required to implement interfaces or methods that it does not need. The ISP is important because it helps us create code that is more modular and flexible. By following the ISP, we can avoid bloated interfaces and reduce the risk of introducing errors and complexity into our code. To understand the ISP, let's consider an example of a class hierarchy. In this example, we have a printer, scanner, and fax class, each with their own methods. We also have an all-in-one printer class, which is a subclass of all three classes and implements all of their methods. However, this class hierarchy violates the ISP since the all-in-one printer class is forced to implement all the methods of its superclass, even if it doesn't need them. This can lead to bloated interfaces and unnecessary complexity in the code. To adhere to the ISP, we can refactor the class hierarchy to use smaller, more focused interfaces. In this refactored code, we've separated the printer, scanner, and fax classes into their own interfaces. We've also defined a new multifunction device interface that combines the printer and scanner interfaces. Finally, we've implemented the all-in-one printer class as a subclass of multifunction device and fax, and implemented only the fax method. With this new class hierarchy, we can now create more specialized interfaces that only contain the methods that a class needs. This reduces the risk of introducing unnecessary complexity and errors into our code. Dependency Inversion Principle, DIP. The Dependency Inversion Principle, DIP, is one of the solid principles in software development. The principle states that high-level modules should not depend on low-level modules. Instead, both should depend on abstractions. In addition, abstractions should not depend on details. Details should depend on abstractions. In simpler terms, the DIP suggests that we should design our software systems in a way that high-level modules are not dependent on low-level modules. This is achieved by using interfaces or abstract classes to define contracts between modules. By doing so, we can create a more flexible and scalable architecture that is easy to maintain and modify. To better understand the DIP, let's consider an example of a class hierarchy. In this example, we have a payment gateway class that defines a common interface for processing payments. We also have two subclasses, credit card gateway and PayPal gateway, which implement the process_payment method for specific payment types. Finally, we have a shopping cart class that depends on the payment gateway class to process payments. However, this class hierarchy violates the DIP since the shopping cart class is dependent on the concrete payment gateway classes. This makes the code inflexible and difficult to maintain, especially if we need to add more payment types in the future. To adhere to the DIP, we can refactor the class hierarchy to use interfaces or abstract classes. In this refactored code, we've defined an abstract payment gateway class that defines a common interface for processing payments. We've also defined credit card gateway and PayPal gateway subclasses that implement the process_payment method. Finally, we've updated the shopping cart class to depend on the payment gateway abstract class. By using an abstract class to define the payment gateway contract, we can create a more flexible architecture that is easy to extend and modify. In addition, by depending on the abstract payment gateway class, the shopping cart class is not dependent on the concrete credit card gateway and PayPal gateway classes. Conclusion. In summary, the solid principles are a set of design principles that encourage developers to write code that is more maintainable, extensible, and robust. By following these principles, we can create software systems that are easier to understand, test, and modify over time. While these principles may require more upfront effort to implement, they can save significant time and resources in the long run by reducing the complexity and fragility of software systems. Thanks for tuning into this video. If you found this content valuable, please give it a thumbs up and share it with your friends and colleagues. And if you haven't already, be sure to subscribe to our channel for more great content like this. By hitting that subscribe button, you'll never miss out on the latest insights, tips, and strategies that we share. So, don't forget to like, share, and subscribe, and we'll see you in the next video.